This video provides an overview of common graph network problems. So far in the series, we've learned how to create graphs and query them. Now we'll learn how to solve them. Conceptually, we can think about solving graph network problems as the following sequence of steps. Our starting point usually is some real-world problem that we would like to solve. Say, for instance, what is the best way to reach a destination from a particular starting point? The first question that we need to ask ourselves is whether we can frame this real-world problem as a graph network problem. For instance, questions around the best path from a particular source to a destination can be framed as a shortest path graph network problem. The next step in our sequence would be to create the graph by converting the existing data, which may be say in a tabular format, into a graph. Once the data is modeled as a graph, we can solve the graph network problem. Common graph problems usually have a few different algorithms that can be used to solve them. Once we decide on an appropriate algorithm to solve the particular problem, the next step would be to implement a solver. Most solutions in the market require a patchwork of tools and complicated processes to implement this sequence of steps. However, in the case of Kinetica, all of these steps are performed in-house without having to move our data between different platforms. This provides significant ease of use and high performance. Now let's briefly look at the different types of graph network problems that can be solved using Kinetica. Shortest path is perhaps the most well-known graph network problem. It is concerned with finding the path from a source node to a destination node that minimizes the combined weights for all the edges in that path. The obvious application of the shortest path problem to a real-world problem would be to find, say, the best route from point A to point B. However, there are many other real-world scenarios that can be modeled as a shortest path problem. For instance, networking problems that involve finding the best way to deliver content to a specific IP address can also be modeled as a shortest path problem. The inverse shortest path problem is concerned with finding the best node to connect to a source node based on weights. A real-world problem that approximates this would be to find the best technician out of a set of options to connect to a job site. The multiple routing solver solves the traveling salesman problem, which is an extension of the shortest path problem. It can be stated as follows. Given an origin and a set of destinations, what is the shortest path that visits each of the destinations once and returns to the origin? The backhaul optimization problem is concerned with finding the best way to connect new nodes to an existing graph network so that the cost of reaching the new node from certain nodes in the existing network is the lowest. Backhaul optimization is commonly applied to solve telecommunication problems. For instance, to find the best way to lay fiber to connect new towers to existing network access points. The all-path problem simply finds all the possible paths from a given starting node to a destination node. The PageRank solver finds the most important nodes in a network based on the number of connections. Kinetica's solver is based on the PageRank algorithm that was developed by Larry Page and Sergey Brin and implemented as the backbone for Google's search engine. Next, we have the centrality solver that uses the Betweeness measure to find the central node in a graph. Betweeness is a measure of centrality that is based on the number of times nodes appear in the shortest paths between different nodes in a network. This can be used to find, say, for instance, the most critical pieces of infrastructure within a network. Finally, the probability rank solver is a variant of the PageRank solver where the probability of transitioning from a particular node to another is explicitly specified using weights. This can, for instance, be used to model churn. Let's say this graph represents 5 different telecom service providers with directions indicating the flow of subscribers between them. The weights indicate the probability that a mobile plan subscriber will move from one service provider to another. We can use the probability rank solver to establish the relative distribution of subscribers over time across these different telecom providers. So to summarize, Kinetica's Graph API allows us to solve common graph network problems without having to move data between different platforms. In this video, we also got a quick tour of 8 different graph network problems that can be solved using Kinetica.